All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1000. Hopefully you guys are doing okay, had a good week, ready to jump in. We're already a few minutes in. There are quite a few people missing today. I'm not sure what's going on, but let us continue. Forge ahead. Let me make sure I can see the chat and everything on this screen over here. Okay. And of course, as is our usual culture, I do encourage you to turn on your cameras and participate and all that. Try to make this feel as personal and interactive as possible. Which, I mean, I have a few more ideas about that at some point I'll try to implement. But in the meantime, as long as you're comfortable, I highly recommend and request that you turn your cameras on. Of course, ask questions when you have questions, audibly or chat-wise. Much appreciated. I think that'll feel a lot better for all involved. So I don't always feel like I'm talking to myself. I don't even know if you guys are alive or not. All right, so let's actually jump in. Today is going to be a regular Q&A problem, regular Q&A class. Right? See some of you. Thank you for your turning on your cameras. So as always, let's just start with some PSAs. So public service announcements. So on Monday we have our 5th quiz. It's the second to last quiz. There's a 6th quiz as well. So Monday coming, you have your quiz number 5. It'll cover lectures 17 through 20. Lecture 20, by the way, is something that you should be consuming at some point today, at least. The last quiz, quiz 6, is actually at the end of November, November 30th. And the second test, which is the last test for the class, in class, is on December 3rd. After that, you'll have a final, and I sent you information about the final exam schedule. And again, I would recommend, if you haven't done it already, this should have been done a long time ago. Make sure you go to that schedule, map out all your finals, make a schedule for everything, know which finals are happening know when all your classes are having tests next, and so on. When are your quizzes, when are your tests? Have everything laid out so you can come up with a plan. You can efficiently start to plot out the next 5 or so weeks of the semester. It's going to be much harder and much more crazy if you don't have a plan and you don't have a timetable in place. So definitely do that. That being said, also, I would encourage you, the last PSA here is to actually fill out that doodle poll that I have for next week, Friday. So there's also already a scheduled time, I don't remember off the top of my head right now, when we'll have a second installment to the study hall tomorrow. But I sent out a doodle poll regarding next week, Friday. So if you can fill that out, that would be great. So the study hall, you know, I think was very helpful. I think was good, and I did give a lot of useful information there. But I drastically underestimated how much time it can take. Because at the end of the day, I'm teaching you guys, or a lot of you, a whole new set of habits, probably ways you never really studied, undoing years of bad habits. It's not really something you can do in like 2 hours, 2 hours and change. So while the last study hall was pretty, I mean, for lack of a better word, I'll say theoretical. So I just talk about, in general, here's how you want to do things, here's how you want to set things out, here are the steps you should take to do what. But at the end of the day, life isn't theory, it's all about the application. The devil is in the details. And over time, I know that not only have students misinterpreted my instructions personally. So there are lots of times I've given students advice over the years, and I realize that they try to follow my advice if they do at all. But a lot of times they would follow it incorrectly because they're trying to apply something incorrectly, or they're using the wrong things to measure where they are. But also, as all of you know, I'm sure you're all human beings and have lived a long time. A lot of people will know what they have to do. Everyone knows they should eat better, exercise more, study more, whatever, but not many people do it, right? So a lot of people don't do things that even they know they should do, because at one level, it's a different thing to intellectually understand what you should be doing. It's a completely other thing to actually apply it in your life, to actually know how to apply it, how to actually stick with a good plan. So the other two study halls I'll be having is more geared towards that. So the second one, I'm going to talk about application, how it would feel like to apply things. And in the third one, I hope that one is a lot more interactive. So I hope you guys will actually try to apply some of the things I mentioned immediately. And so in a week and change from now, you'll be able to tell me, okay, well, I tried to do what you said, but this didn't work, or I still did bad on the quiz, even though I tried to do what you said, or whatever, just whatever issues you're having trying to implement some of the ideas. I think the third installment of Study Hall would be good to deal with those. So sort of a Q&A. I can leave everything sort of anonymous, just so you don't feel like I'm picking on anyone, but for sure, send me your issues and I'll make sure to address them. But in order to do that, you'd have to start actually trying to apply to the best of your ability some of the things that I mentioned. And so, yeah, try that so you can know. Because sometimes, like I said, it's all in the application and the devil's in the details. You might think you know what I'm talking about, but when you actually try to put it into effect in your life, it doesn't seem to work. The theory doesn't seem to land. So we need to make sure that we can address those issues when they come up. All right. That being said, I think those are all the public service announcements. Moving forward, just want to talk a little bit more in detail about the quiz next week. On Gradescope, obviously, at the beginning of class session, obviously. But the essential things you have to know. So it's lectures 17 through 20 that are covered. In terms of the section breakdown, I think this is all of them. So 2.2, specifically just the part of 2.2 that dealt with piecewise functions. I already quizzed you on the rest of 2.2 last week. 2.6, 2.8, 3.3, 4.1 and through 4.4, which means 4.1, 4.2, 4.3, 4.4. There are two more sections in chapter 4. We have 4.5 and 4.6, but that is not covered in lecture 20. That is covered in lecture 21. And it might spill over a little bit into lecture 22 if memory serves. So those are the sections. Okay, as for the actual topics that you would need to know. So piecewise functions, you need to know about piecewise functions, what they are, how you graph them, how you'd evaluate them. We've actually done that in the bonus section of a couple quizzes before, so that you should be okay with, I think. Transformations of functions is another one. And for the most part, these are just rules that you guys should know. This basically talks about shifting and stretching functions, how that would work. If you make certain arithmetic adjustments to a function, how does the graph react, right? So if you have f of x and you add 5 to everything, f of x plus 5, what happens to the function? Or if you go to the function f of x and you replace all x's with x minus 5, what happens to the function? So that's knowing how to shift vertically or horizontally, or to stretch or to rotate functions. That's what transformations of functions is talking about. So mostly the graphical thing, but you should actually be able to connect the arithmetic operations to certain things that would happen graphically. Inverse functions, the next topic, very big topic. You should know what they are, what their properties, how to actually graph them, how you would find inverse functions. So if I gave you a function and I told you that it's invertible, how do you actually go about finding the inverse? And also, if I were to give you two functions, f and g, and I were to ask you, are these functions inverses of each other? You should know how to actually check and verify that they are inverses, or be able to conclude that they're not inverses of each other, that sort of thing. Should also know about one-to-one and onto functions. These are two properties of functions may have. Whenever a function has both of these properties, that's how you know the function is invertible. A function that does not have one or both of these properties would not be invertible. You will not be able to actually find the inverse. One-to-one, couple ways you can check there. There's the graphical check. So one-to-one would mean that it's a function that passes the horizontal line test. So again, all functions pass the vertical line test, but one-to-one functions are functions that also at the same time pass the horizontal line test. So any horizontal line you draw will touch the function at most in one location, right? So that's what a one-to-one function is. There's also a formulaic way to verify one-to-one. If you don't know the graph or you don't want to draw the graph is too complicated, you can actually use calculations to determine one-to-one. So we covered that as well. Onto functions, so one-to-one functions or 1-1 functions, aka injective functions. Those are all the same thing. Onto functions, another name for those guys are surjective functions. And these are just functions in which the codomain is equal to the range. So you have the domain, the set of all things you want to assign values. There's the set there where you want to assign their values from, that's called the codomain. If everybody in the codomain is the output of someone in the domain, we call such a function onto. So it means all possible output values are attained. You won't have a set where the function misses some people. So you look like at, say, if you thought of your codomain as the real numbers, we're thinking of the outputs as it could be any real number, then the function y equals x squared is not onto because it would miss all the negative numbers, right? So you can't have x squared equals to a negative number, for example. So that function would not be onto, whereas a function y equals x cubed would be onto. You'll actually hit every real number as an output by that function. Another thing, very important topic, long division of polynomials. So we learn how to divide polynomials, and not in the sense that, oh, you factor and cancel, but in the sense that even if you can't factor and cancel, there's still a way to actually divide polynomials. That is long division. It's actually very, very important. Even this semester, I had some problems in Calculus 2 where the students had to be able to do the long division to actually do the problems, and a lot of them didn't remember it. So definitely you want to remember long division. There is another game in town, so let me just mention that. When it comes to long division, or another thing that's often used here is synthetic division, which you may have learned in high school or something. But I didn't really go over that in class for several reasons. So let me just actually mention that here. So synthetic division, not done in class. However, I'm usually not one of those people who it's like my way or the highway. So you can use alternative methods. So if you like synthetic division, you can use it. I will recognize that you're doing synthetic division and you'll get full credit for it. So whenever you can use it, you can do that if you want. Not done in class, but you may use it when appropriate, without penalty. Now, of course, because I only covered long division, I might have some questions where it specifically talks about long division. And so if you're really partial to synthetic division, at the very least, you'd have to understand long division enough to the point where you know what step in your synthetic division calculation would be analogous to which step in the long division calculation. So you should be able to figure that out as well. So know how to connect the two in case I ask you something that is specific to long division. And as you guys know, I often show you guys multiple ways. So even though personally, if I'm factoring quadratic, I always use like the trial and error method. I did go over the AC method with you guys. I did go over the payback method with you guys, because in general, I don't care what method you use. However, you'll notice that synthetic division is another game in town, but I still did not go over it in class. And the reason is the following. Synthetic division actually will not work in all cases. So there are situations in which synthetic division will not work. And there are also some simple cases in which synthetic division can work, but you'd have to modify it somehow. So for one, the thing is synthetic division only works if you're dividing by some sort of linear function. So if you're dividing by x plus 5 or 3x plus 1 or something like that, you can use synthetic division. If I ask you to divide one polynomial by x squared plus 2x plus 7, can't use synthetic division anymore. Doesn't work, right? So because it was such a limited method, I decided just not to talk about it at all, because then now I'm just introducing ambiguity, where it's the point where, yeah, you guys know two methods, but now you also have to know when one of the methods won't work. It was just too much. So I just decided to not talk about it at all. It is a valid method in some situations, but it won't work in all situations. There are also situations in which it can work, but you'd have to modify it. So for example, if I were dividing by x plus 5, I can apply synthetic division the way that most of you would know it. If I asked you to divide, however, by 2x plus 3, then you'd actually have to modify synthetic division, and you'd have to recognize that you need to modify it. You can't actually apply that directly. So synthetic division will only work if the coefficient of the x term is 1, which means if I ask you to divide by 2x plus 3, the first thing you'd have to do is factor off the half. You'd factor off the 2, which essentially becomes a half on the outside. And then you'd have to write it as x plus 3 over 2. And then the 3 over 2 is the number that you would use in synthetic division. So you'd have to know how to modify it like that. So synthetic division just has all these little nuances to it that it wasn't worth it to me to actually go over it. So you can use synthetic division, but you use it as your own risk. Make sure that when you're using it, you know you're in a situation where you can use it and you know how to modify it. So it does not work in all cases. It works if dividing by something like x plus a, where a is a constant. It can be modified to work. If dividing by something like ax plus b, where your a is not equal to 1. And of course, your a can't be 0 as well. But if your a is not 1, you kind of have to factor it out to get it to work, and you have to divide the b. So you'd actually think of it as you're dividing by x to the plus b over a, and the a you have to remember to multiply at the end. And it won't work in all other cases. Okay. So just because it was just such a nuanced method, it's an alternative to long division, but it's only an alternative to long division in a few situations. And half of those situations, you'd have to modify the method and work with fractions anyway. Yeah, to me, it wasn't worth it as a viable method. So yeah. If you're in a situation where you can use it, you know how to do it correctly, do it. Be my guest. I'm not going to punish you for that. Just be aware that if you do mess up, or I ask you about something where it cannot work, you need to recognize it, and you'd probably have to use long division anyway. So just learn long division. It's a better method for more reasons than just personal preference. Like it's objectively the better method. It applies to more cases. So it's not even a personal preference kind of thing. It is like, it's objectively the better method. Long division is better. So yeah, so I'll just say something about that. So topic 6, as you see here, rational roots theorem. So you need to know the rational roots theorem and know how to use it to factor a polynomial. So we've learned about all sorts of methods of factoring here. So, and we know general approaches of factor out the GCF. And if there are 3 terms, it looks kind of quadratic, you try like the AC method or something like that. Or if there are 4 terms, maybe you try factor by grouping if that didn't work. Or so. So we understand in general, but there are times when you would have a polynomial where none of that seems to work. And the rational roots theorem can actually help you factor a polynomial. So we did a couple examples of that in class as well. So know what the rational roots theorem says, how to apply it, and how to use the rational roots theorem, in addition to the factor theorem and some other theorems that I gave you, to factor a random polynomial when none of the methods I told you before work. Another thing that came up in Calculus 2 that the students couldn't handle this semester that I had to remind them. Exponential functions and the natural exponential, these were also things that were spoken about. So by the natural exponential function, I'm talking about the function y equals e to the x. This is a very important exponential function, the most important exponential function for calculus. And there are a lot of math people, even ones much smarter than I, who believe that y equals e to the x is the most important function in all of mathematics. So there are those of you who may become math majors, I don't know, but there's a textbook that is infamous about math, when it comes to math majors. Like everyone knows about that textbook, it's a legend, and everyone knows it's insanely difficult, and everyone has some experience with the book. It's very divisive. You either love it or you hate it. And yeah, the prologue of that book starts out with introducing the function y equals e to the x and starts with the statement, this is the most important function in all of mathematics. It's a very important function when it comes to Calculus 1. If you're going to do Math 1206, especially, myself and a lot of other instructors will derive a lot of the rules that you would need for that class using exponentials and log functions. Very important functions, you can derive a lot of things from it, and it's super important. Exponential functions in general are functions that look like a to the x, just a constant raised to the x. We normally assume that the constant is positive. That's because having a negative base can give you complex numbers and all sorts of things that I don't want us to have to deal with. So we normally consider a to be a positive number. If a is 0, 0 to the x, we just think of it as 0, except if x itself is 0. As well as if a is 1, we also don't really consider that because 1 to the x is going to be 1 all the time. So we think of it as positive numbers. We don't include 0, we don't include negatives, we don't include 1 because they're just, the negatives are just really tricky to deal with. The 0 and the 1 are just trivial. It's kind of like having a constant function, except it has a hole in one point in the case where the base is 0. Right. So you should know their graphs, what they mean, etc. We also covered logarithms. So logarithms, I told you what those guys are. It's another way to look at exponential equations. It's like if you want to solve for the power in an exponential equation, you would use logarithms. So I talked to you about logarithms and log functions. When it comes to logarithms, I told you the 10 important rules to know. The first 5 of those were absolutely important, mandatory. You have to know them. The last 5, you could derive if you know the first 5, but I highly recommend you just memorize them anyway because it's just, they're useful things to know, right? And it will come up, it'll actually, if you've been studying correctly, the rules will come up so often that you'll end up memorizing those last 5 anyway. So if you're in the situation where you don't remember those last 5 rules and you've never specifically dedicated time to remembering them, it's probably an indication that you're not studying enough, because they come up often enough to the point where even if you don't specifically decide to remember them, you're just going to remember them because it'll come up so often. So things like log of 1 equals 0. The logarithm of 1 is always 0. That's just something you should know. It's something you could derive from the definition, but it's just also something, log of 1 is 0. I just know that no matter what the base is, log of 1 is 0. Knowing that log of 0 is undefined. or log of any negative number is undefined, right? So these are just things that you would just know. Again, you can derive this from the definition, but again, it's just something that you would know all the time. You're dealing with functions, you're going to talk about their domains all the time. You're going to know that, oh, I can't plug in negatives here, right? So you'll know, right, if you've been practicing enough. One thing that important idea was that the logarithm functions and exponential functions, when they are based on the same base, they're actually inverse functions of each other. So y equals log to the base a of x is actually the inverse of the function y equals a to the x. And yeah, knowing that is something that you should know at this point, and you should be able to apply that to simplifications. You will need that knowledge in a different way in upcoming sections. So that actually will help us when solving exponential and log equations, which technically is not on the quiz, but it will be in the bonus section of the quiz. So you should can make a note of that. If you just push a little further into lecture 21, I talk about solving exponential and log equations. I also talk about graphing exponential and log equations. So that would be stuff for the bonus material, sections 4.4 and 4.5. Or I think that should be 4.5 and 4.4. 4.5 and 4.6. It's a typo. I'll have to fix that later. And so, yeah, what else do we know? Right, so knowing that exponentials and logarithms are inverses of each other, it means you can essentially use one to cancel the other one, right? And there were actually log rules that told you this. The rules 8 and 9, I believe, that I introduced in class actually told you this. So it kind of means like if you have an equation and there's a logarithm in there and you want to get rid of the logarithm, you'd use an exponential. If you have an equation and there's an exponential in there, then you can get rid of the exponential by trying to write both sides to the same base. But in all cases, including when such a method will not work, you can take logarithms and that will work. So logarithms can cancel exponentials, exponentials can cancel logarithms. They're inverse functions, and hence you can think of these guys as inverse operations. Similar to how if you have an equation and you want to solve for something, you know something is being added to it, you have to subtract that thing from the both sides, because subtraction is the inverse operation of addition. If something is multiplying by the thing you want, you divide both sides by it, because division is the inverse operation of multiplication. In a similar way, if you have something stuck inside an exponential, you can log both sides, because that would be the inverse operation. That's how you'd solve for that thing, and vice versa. So that's pretty important to know. And you need to know how to simplify exponential and log expressions in general. So if I give you the logarithm of a big complicated mess, you should know how to break it up into smaller logarithms, simpler logarithms. If I give you a sum of simpler, smaller logarithms, you should know how to build it up into a big logarithm. If I give you an exponential and something is a huge complicated mess, you should know how to simplify it. Yeah. And that's what you would need to know for the quiz. So, I mean, if I was just talking, I mean, I already taught you about these. So if I'm just talking and anything I mentioned, you realize, I don't think I know how to do that. That's probably what you want to ask me about moving forward. So I just did a quick summary of each of these topics, just to let you guys have an idea of what I mean when I say it, so that you'll know whether you know that or not. Yeah, I know how to do that, but I don't think I know that, right? So hopefully that was helpful. When it comes to the material following the quiz immediately, so what would count for bonus material? This would be exponential and log equations, graphing exponential and log graphs, knowing where their asymptotes would be, how they would look, knowing how to sketch them. That would be stuff for bonus, as well as we started in lecture 22. I want to say we started talking about angles and trigonometry and trig functions and all that good stuff. So if you remember about your trig functions or angles or trigonometry, or you went ahead and you watched those videos, you can probably take a shot at a couple bonus problems with that stuff. Okay, yeah. So that's essentially going quickly over the quiz topics, the materials that I expect you to know. And at this point, what I would say is it's time for Q&A time. So thinking about these topics, anything that was mentioned that you're not quite sure about, that you'd like me to talk about, maybe emphasize the important points of, you can let me know. Maybe you've started some of the homework, you got stuck on something, you don't understand something, you can ask me about that now as well. Or I guess just any general concerns, questions, comments. So give you guys a few seconds to actually collect your thoughts there and let me know. So just thinking about these 9 topics here at least. Anything that is potentially an issue, now's the time to deal with it. And also it's, as you'll notice now, and it'll be like that for the rest of the class, it seems like we're just going through a lot faster than we did before. So we're going through a bunch of topics. We learn about piecewise functions, transformations, inverse functions, long division, exponentials, and log, like so many things in such a short time. And it's because, like I mentioned, I went very slowly through chapter 1 because it is the foundation, it is the basics. And when you understand those, you will understand these guys. So all the simplification rules that would apply to all of these things at any given time, we are doing some sort of rule that I already taught you how to do. And so we're just applying that to different scenarios. So now I can just introduce a lot of new novel ideas, because how you deal with those ideas once I define them is based on chapter 1. And so, yeah, pre-calc, like I said, is a basic foundation for calc 1, calc 2, etc. I see a lot of my calc 1 and calc 2 students having trouble with these things that I'm talking about here. And so, yeah, not understanding pre-calc is going to come back to hurt you in calc 1 and calc 2. And it's going to hurt you in secret. If you're not good at pre-calc, you're not even going to realize why calc 1 or calc 2 is so rough for you. It's one of those things where because you're in calc 1 or calc 2, you're going to think that, oh, my problem is calc 1 or calc 2. But the truth is, if you're having trouble in calc 1 and calc 2, 99.9% of the time, your issue is with pre-calc. It's not calc 1 and calc 2. Students usually catch on to the calculus part relatively easy, actually. It's these things that they're forgetting. And similarly, if you're having trouble in this class with anything, then it means your chapter 1 is what's messed up. If you don't know your chapter 1, everything else is going to be hard. And that's why I spoke about chapter 1 at such great length. So hopefully you guys didn't just roll your eyes and not pay too much attention in chapter 1, because not understanding chapter 1 is not only the issue that's going to bite people in this class, but it's going to bite you for the rest of your calculus career, quite literally. A lot of the mistakes that I'm seeing in my calc 1 and calc 2 classes are from these topics. So try to get prevention is better than cure. Make sure you try to get on top of these. And once we introduce the trig functions, you'll notice that we have learned about 6 different classes of functions for the most part. So we would have learned about polynomials, rational functions, radical functions, exponential functions, log functions, and trig functions. And of course, you can create functions by combinations of all of these, by adding them, multiplying them, dividing them, composing one, plugging one into the other. And all the functions that you can get by this kind of combining of these 6 guys, these are called the elementary functions. And they are the guys that are the foundation of, again, all of calculus. You'll never really need to know about any other functions in great detail for the rest of your calculus career. The moment you're introduced to new functions, it's going to be a class above the calculus level, and they're going to get complicated. So right now, these 6 types of functions, they're like the infinity stones of functions, right? These are the building blocks. Everything else is connected to these. And whatever it's not connected to these, we usually have a lot of trouble with those things, or we just have to make up stuff so that we can continue studying math from it. So yeah. So that being said, questions, issues, comments, concerns?
Do you mind just walking through topic number 6, please? Like just going into detail for it a little bit.
Rational roots theorem and using it to help you factor polynomials. Okay. Cool. So okay, so just a quick run through the rational roots theorem. So this is basically saying if you have a polynomial, let's say it's an x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a2 x squared plus a1x plus a0. So it basically says if, and this is a if this has rational roots, then they must be of the form x equals, it could be plus or minus the factors of the constant term divided by the factors of the leading coefficient. Now, remember what a root is? It is a number that you can plug into the polynomial to get 0. So it turns out, if you want to know what are some fractions, so rational, remember rational roots just means roots that are fractions. And by roots, let me just be specific, fractional zeros of the function. I mean, these are fractions that when I plug into the function, the output is 0, right? So that's what we're calling roots, right? These are the same as the zeros of the function. It's saying that if there are any fractions that would make the polynomial equal to 0, then the fractions must have this form. So example, if p of x equals, let's say 6x to the 5th minus 7x cubed plus 2x squared plus 5 has rational roots, then they must be among, I don't even know if it has rational roots. It's possible that it does not, but if it does, it would have to be of the form plus or minus factors of 5 divided by the factors, or not factor, factor of 6, right? So the possible rational roots here is all possible roots of 5 are 1 and 5. So it's either 1, 1, 1 over 2, 1 over 3, 1 over 6, or it's going to be 5 over 1, 5 over 2, 5 over 3, or 5 over 6. So if there are any fractions that would make this polynomial output 0, it has to be one of those guys. No other fraction would make that number 0. Okay. So that's basically what the rational roots theorem tells us. And there's something called the factor theorem. And this basically says P of X is a polynomial if X equals A is a root. I remember what that means. This just means if I plug in A, I get 0. Then X minus A is a factor. And that would mean i.e. P of X factors into X minus A times something. Right, so you know that you know that your polynomial, it's possible to factor it, and you know exactly what one of the factors is. So that's called the factor theorem. Now, these of course are guys you should know, and I might quiz you on just whether or not you know what these theorems say. But one important application is being able to actually factor a polynomial. So maybe I should go over that. An important application of the above is to be able to factor a polynomial. So let's actually jump through an example there. And while we're doing this, we can actually practice long division at the same time, because long division is what you would actually use to actually figure out what these guys are. So for a problem like this, I could come up with an example in my head, but I don't want to have to. So I'm going to have our textbook here. I'm going to grab a problem from over here. Came prepared. Let's see, what section was this in? Okay, so this is 3.3 for any of you keeping track. Let's actually find a problem here. So something different from what I did in class. I wanted one that was had a little trick in it that I would think of doing in a quiz, but I don't really see any of those. So I guess I'll just give you a random example, and then I'll mention to you something that could come up that I'll probably try to pull off, probably try to pull over your heads in a quiz. So let's actually, example here. Hopefully this factors completely. I didn't even check. Factor x cubed minus x squared minus 11x plus 5 plus 15 using the rational roots there. hopefully that factors into something really nice. Put this down over here. Okay, so here's something, right? So normally you see something like this, it has 4 terms in it, so you'll probably think, oh, maybe factor by grouping could work. And you'd quickly realize that factor by grouping would not work. Because you factor out the common factor of the first 2, you're left over with x minus 1. If you factor out the common factor out of the last 2, you're not left with x minus 1. And rearranging the terms here won't help you. So yeah, what is this factor as? We don't know. However, we can do the rational roots theorem. If I think of this as P, the first thing I would do is try to find the rational roots. So then I would say the possible rational roots. Okay, so maybe some of you guys can help me out here. What are the possible rational roots? So this might be a quiz question here. This is actually a pretty nice quiz question. I can give you a polynomial and ask you, what are the possible rational roots?
Of 15. Are you starting like with 15?
Okay. What else?
Oh, 1.
Five and 3.
And? Is that it? It's not correct. What's missing? So this is what the rational roots theorem says. So looking at that, what's missing? And probably another comment I would make is you guys are kind of all over the place here. I foresee it being possible that even among these numbers, you guys probably, based on how you are thinking of them, could miss some. I don't want you to do that. So you should have some sort of systematic way in which you are thinking about these numbers, from like smallest to largest or something. So make sure you don't miss any. So probably what I would notice here is that my AN term is just 1, which means the factors here, well, it's just 1. And I would notice that my A0 term here is 15. And then I would look for the factors, right? So 15 factors into 1 times 3 times 5. If I were to factor the prime factorization. Which means its factors are 1, 3, 5, and 15. Right, because you can get the factors by just multiplying all possible combinations of the prime factorizations, right? And of course, the important thing you guys forgot is you can have these guys being plus or minus. You do want to take signs into account. So it means, therefore, there's only one possible denominator, so it's always over 1. It's always going to have a plus or a minus here, so that's the second thing. And then I just cycle through all possible factors of the constant term. So for 15, it could be a 1, a 3, a 5, or a 15. So that means plus or minus 1 possible, plus or minus 3 possible, plus or minus 5 possible, plus or minus 15 possible. So those are all the possible rational roots. If there's a fraction that makes that polynomial 0, it's one of these guys. So now what you do, so the first thing you want to do is find the possible rational roots. And this could be a question in and of itself, right? This is definitely like a quiz question to me. And then, but let's say we're fully doing this problem. So one step into this problem is something that I would actually literally ask as a problem unto itself. But this is only the first step of this particular problem. Once you do that, now you need to find a root. Right? So you're going to find P of 1, P of, say, minus 1, P of 3, P of minus 3, etc., and try to get 0. Now, it's not always going to, there's no indication of who would actually get it to work. So this part is almost purely trial and error. However, you can normally figure out some situations here. So you can have an idea if you actually plug in certain things, what would likely not work versus work. So I would actually recommend to try the 1 and the minus 1 all the time, always anyway, because it's really easy to check, right? So if you were to plug in the 1, right, you would get 1 minus 1 minus 11 plus 15, right, which is not 0. Plug in a minus 1, you would get minus 1 minus 1 plus 11 plus 15, not equal to 0. Right? So you're literally just plugging in these numbers, okay? So the smallest numbers didn't work. Let's go up to the next biggest number. What if I were to plug in 3? So this is 3 cubed minus 3 squared minus 33 plus 15. Okay, what would that be? 3 cubed is 27 minus 9 minus 33 plus 15. 33 minus 9, what is that? Is it minus 44? No, 42. Right. So I take minus 42 and I add 9 to that, I would get minus 33. And now if I take 27 plus 15, I get 42. So this equals 0. So this means x equals 3 is a root. And that means by the factor theorem, x minus 3 is a factor. And that's the important part. That's the break we needed. Okay, thanks, Angelina, for letting me double checking my work here. So we do get 0 in that situation, both me and Angelina. Okay, so what does it mean that x equals -3 is a factor? So once you notice that, you are immediately going to jump to, now you're going to move on to the divide stage, which is where a long division is going to come in. You're going to take that x -3 and you're going to divide it into the original polynomial. So this is x cubed minus x squared minus 11x. Speaking of the trick, which I mentioned, that could occur, that I might even throw at you guys, it's not really a trick, it's just something you should know, is the initial setup is very, very important in the sense that you need to make sure that all powers of x from 3 to 0 must be accounted for. Use a placeholder if necessary. This is very important. You're going to want things to line up. If you don't have things lining up, it's possible for a very silly mistake to actually crop in and get you the wrong answer. So for example, if the -11x were not there, right? So let's say it was just x cubed minus x squared plus 15, like I have written here, you would literally write in a 0x. You need to have that position for the x there, right? So you don't just stick the plus 15 right beside the x squared. You're going to run into trouble. You want a placeholder for all powers of x from the highest power all the way down to 0. If you don't line these guys up, there's a risk of making a big mistake. So that's very important. And so that might be a trick that can come up. It's not really a trick, but if I'm giving you a problem like this in a quiz, I'll probably deliberately have one of the powers missing just to see who is actually lining things up correctly. And then I'll probably put one of the answers where a particular kind of mistake would occur to give you that answer. So just remember that. So we do need all powers accounted for. Okay, so that's the first thing. Okay, so now we're actually going to go through and do the long division. Maybe someone wants to do the long division with me. How do I go about this?
You multiply by x squared first.
What do you mean multiply by x squared? Where would the x squared come from?
You put it above the x cubed, so you get x squared times x equals x cubed. So it can't.
Yeah, but where the x squared come from in the first place?
When you multiply.
You said there should be an x squared in top, which I'd probably line it up above the x squared, but why is that an x squared? Why wouldn't it be an x? Why wouldn't it be an x cubed? Why x squared?
Wouldn't it just be x because x times x is x squared?
So you think it should be x?
Mm-hmm.
Right, like that's what I'm asking. What should it be and why? How did you get the first number?
I think she got x squared because x squared times x is x cubed.
Right, but which one should it be?
It's x.
I think it's x squared. Because if you're trying to get to x cubed.
So we have like a civil war here. I'm thinking of that meme where it's like Captain America is like X and then Tony Stark is like X squared and then it's like civil war. Okay, no. So again, you have to remember how long division actually works. The first guy comes from, so this is why I want to ask you, because I know some people would have a different idea of why, and so there's a possible disagreement that could occur here. The first guy comes from taking the first term here in the divisor and dividing it into the first term there. So what you should be writing on top is what you would get if you take x cubed and divide it by x, right? And so now you know x squared is what should be on top, okay? So x squared should be on top. I'm just lining it up with the x squared. You could put it on top of the x cubed if you want, but I went through this whole thing about lining everything up just now. I just want to just going to keep everything lined up. So yeah, so x squared should be the first thing. But again, it's very important you know why that's the case. It's because you took the first guy here, divided into the first guy there, right? And you get x squared. Now, when you have that x squared on top, what do?
You write x minus 3 underneath the x to the third minus x squared.
No, that's not the second step.
You would multiply the x minus 3 by x squared so that it becomes
Right, so you're going to
x
take
cubed.
this and you're going to multiply those, and then you're going to put the answer underneath this, making sure to line up with everybody. Right? So I take the x squared times the x, I get x cubed. Then I take the x squared times the minus 3, I get minus 3x squared. I line up the x cubed and the x squared right underneath the x cubed and the x squared. And then we subtract from the line above. Then so that means I would have x cubed minus x cubed, those guys die. Then what I do is now I would have a minus x squared plus a 3x squared, because it's minus a minus 3x squared. So it's a minus x squared plus a 3x squared, and I get 2x squared here. Okay. Or is everyone with me so far? So you get the first guy by taking the first guy in the divisor, dividing into the first guy in the under the sign. Then you write what that result is. Then you take that result, you multiply everyone in divisor, you line it up underneath, and you subtract it. So you get this. Now, once you get that 2x squared, now what do?
You're going to bring down the, like, it'll become 2x squared minus 11x plus 15.
Okay.
So you want to, like, bring down everything.
Okay, I can do that later, but yes, eventually. But then what? After you do that, what would you do?
Multiply the x minus 3 by x so that it becomes x squared, or by 2x so that it becomes 2x squared, and they can cancel out.
You're skipping a step again. Where did 2x come from?
You multiply it by 2x so that it becomes 2x squared minus 6x. What?
Yeah, but why? Where did
What do you mean?
you said multiply by 2x? Where's the 2x coming from? Like you just mentioned a 2x and you didn't explain where it came from.
What do you mean where it comes from? Don't you just multiply it so that it becomes 2x squared, so that the 2x squared will like subtract and equal 0?
Okay, so if this were 3 over 2x squared, what would you multiply by?
3 over 2x.
And if this were 3x to the 7, what would you multiply by?
3 over 2x to the 6.
Okay, and if this was x to the 9th and this was an x squared up there, what would you multiply by?
Isn't it 3 over 2x to the 7th?
Yes. Right, now this is what I want to get at. Why is that the answer? Because clearly you can see there are situations where you can just randomly, you can guess because you can just, the numbers are nice. But yet if I change the numbers, suddenly you don't know what to do. That means there's a concept that you don't understand. So again, just like how I asked, where did the x squared come from? Right now I'm asking you, where does the 2x come from? You need to know, because if the numbers aren't nice on the quiz, or there's a trick, when really there isn't no trick, it's just, you always get the numbers the same way. If you don't know the concept, like where the numbers are supposed to be coming from, that's what's going to trip you up. This is why students are like, oh, the test is nothing like what we did in class, when it's not true. Like, you learned in class the method. So it doesn't matter what numbers I put, if they're fractions or not, it shouldn't matter to you. There's a concept that you're supposed to be doing.
Are we supposed to do 2x squared divided by x?
Yes. Once you do this step, it's literally a rinse and repeat of the previous set of steps that we did. Meaning, you're going to take the first guy here and divide it into the guy here. The result of that division, 2x squared divided by x, is 2x. So that's where the 2x came from, right? You need to know that that's where it came from. It's not just something random or something nice, or I can see it, I can eyeball it and see that that's what would work out. No, I know specifically it came from taking this and dividing by that, right? So hopefully you understood the first set of steps that I did with the x squared and all blah, blah, blah. You literally rinse and repeat now. You keep repeating this until you get to the last term. So I'm going to take the x, divide into the 2x squared. That gives me 2x. I'm going to take that 2x and multiply the x minus 3. That's going to give me a 2x squared minus 6x. Then I can worry about bringing this down, because now I'm starting to combine things. The 2x squared cancel each other. Then I'm going to have minus 11x plus 6x. So that leaves me with minus 5x. What do I do now? Rinse and repeat. X divided into the 5x is minus 5. Take the minus 5, multiply everybody. Minus 5x plus 15. Bring this guy down to combine. The minus 5x's are going to cancel each other. And now I have plus 15 minus 15, so I get 0. Okay. Make sure you know the process of long division. Very important, where the numbers are coming from, because then this is one of those situations, and this is very important. It's another lesson, I guess. You could bring this. This is like one of those pro tips from you could put in a study hall question. Because what's possible here is that you could practice a bunch of problems where all the numbers were just nice. And so you got them all right because you can kind of guess and make up some number. And so you practice a bunch of problems and you did okay with them. You got the answer, but then you go into the test. And then the test had just a weird number in there. And suddenly now you're confused. And then you ended up getting that problem wrong in a test when in practice you were getting it right. And then you're like, I don't understand what happened. I felt ready for the test, right? This is why it's very important that you don't just know how to get an answer. You know, why was that the answer? What was the first step? What was the second step? Where did this number come from? Do I know how to get that number? Can I check my work, right? You do want to make sure that you can deconstruct an answer. You can deconstruct a process into the individual steps, right? And there are a few times in class that I showed you guys this. We actually also did it when it came to factoring. When I asked you guys to factor a quadratic, everyone knew how to do it. But when I put the power 3/2 and then 1/2 and then x to the minus a half and asked the class to factor it, no one knew what to do. It's because they didn't understand the concept of factoring. They didn't understand what steps there were to take. They didn't really understood what it means to find a GCF and factor it out, right? And it meant you subtract from all the powers, right? So there are times when you can just kind of wing it because it's just easy to see, but that's not math. Math is knowing about the strategy and the reason and the logic behind something, right? So that's what you want. You want to be in a situation where If I ask you a problem like this, you get it correct, no matter what. Whether my numbers are ugly or nice, it does not matter. You know how to do this problem. There's nothing I can throw in there that's going to trick you, because you didn't get it by happenstance because you happened to practice with nice numbers. You got it because you knew exactly what's going on. You know exactly where each number is coming from. You know how to construct the numbers that you would need to get the problem solved. Very important. I don't want to elaborate too much because we're actually a little bit over time. So let's actually wrap this up. You must get a 0 here. Otherwise, you made a mistake. And it could come from you not lining up things correctly or whatever, but you should notice when something is off. You should get it in this scenario because we know that x minus 3 is a factor. And by the factor theorem, we know that that means that the remainder must be 0. Well, there's actually another theorem that tells you that. But yeah, you have to get a 0 here. And so what this basically means is that the original x cubed minus x squared minus 11x plus 15 actually factors into x minus 3 times the guy that we call the quotient here, x squared plus 2x minus 5. And then, of course, we know we should check if this factors. And it doesn't. So these are the factors. So this is the factorization. So of course, personally, I would give you something where the quadratic itself would factor further. So I know I can factor this guy as this. And it can't actually factor any further. So that's how you'd use the rational roots theorem. That's what it is, how you'd actually apply it. So you can find what the possible rational roots are. You keep plugging them in. If it's possible for this guy to factor based on that, you will get 0 as a result for one of them. Just start at the smallest number and work your way up. And then you would do the long division. So whatever x value you plugged in to get a 0, x minus that value is going to be a factor. Do the long division, make sure you understand how to do long division, and you should get a 0 as the result. Otherwise, you made a mistake. Either you made a mistake up here or you made a mistake down here. But if you don't get a 0, it means something is wrong. It means that thing is actually not a factor. Once you do that, it means that the guy under here will factor into this guy times that guy. Right? And in your homework, they call this guy d of x. They call this guy q of x. They call this guy p of x. And they call this guy r of x. So there was some homework problem where they actually gave those names to it. So just so you know. Yeah, but that's how you'd factor this polynomial, right? So we couldn't factor it based on any of the techniques I showed you in chapter 1. But now, because we know long division and the rational roots theorem, we have more machinery. We can factor more complicated problems. Now, since we're out of time, we are going to end there. I will say the following, that my earlier class, pre-calc, this same class, had a whole different set of questions for me. So it might be worth you watching that lecture as well. So that's the class I had at 11:30 this morning. So it might be worthwhile to watch that as well, because I also spoke about long division with them, but for a different reason. But they also asked some questions about inverse functions. They asked me to go over a homework problem, and they asked me about one-to-one and onto functions. So especially if you're kind of iffy on those, it's worth probably watching the other lecture as well, in addition to lecture 20 today. We are going to wrap up there. Have any questions? Of course, you can let me know before Monday. And for now, I guess I think that's it. I think we are we're done. All right, so have a good day, everyone. It's very gloomy and overcast. It's one of those days where you want to stay in bed. If you're going to take a nap, take a very short one and get back to work. Good luck on the quiz next Monday. Fill out that doodle poll and make sure you know the schedule for all your classes, your tests, and your finals and all that good stuff. And with that, we will end. I will see you guys in the next one. Ciao.